Good morning, student. So welcome to Urban Pro. Today's session, I'll be discussing on Faraday's law and Lenz law. Okay, what Faraday says is, suppose we have a magnetic field. So these are the magnetic field lines. I'm drawing only 3 to 4 arrows which represent magnetic field. And in this magnetic field, suppose we have a coil. Okay, this is a closed coil or closed loop. Now there is some flux associated with this coil due to this magnetic field. As we know, flux phi is equals to B, that is magnetic field, and the A vector, that is area vector. If B dot A gives BA cos theta. What is this theta? Theta is the angle between this. Suppose this is the angle of the this is the area vector n cap, and this is the P is this one, red one, and the angle between this magnetic field and the cross-sectional area vector is theta. Then phi is BA cos theta. Okay, so the Faraday's law says, suppose the change in magnetic flux associated or linked with a coil, when the magnetic flux associated with a coil changes, then some EMF is induced in this coil. Okay, this is all about this Faraday's law. So when this EMF will be induced in the coil, definitely some current will be flows through the circuit or coil or the loop, isn't it? So let us write what is Faraday's law. This is Faraday's law. It says whenever a magnetic flux linked with a closed loop or closed coil or circuit is changed, an EMF, that is electromotive force, is induced. Okay, is induced, and it lasts up to last until is last until the flux is not constant. That is, whenever there is a change in flux, there will be an induced EMF associated with the coil. Okay, so see, let us see through some examples as I already given. Suppose this is a magnetic field lines. Suppose I draw only two magnetic field lines, and here I have a coil. Here I have a coil or loop, and I attach here a galvanometer. Okay, which is deflected when current passes through the galvanometer. So now no current is flowing through the loop, so the deflection is, there is no deflection in the galvanometer. Now suppose I will change now this magnetic flux. How will I change the magnetic flux? Let me copy this. Anyhow, suppose I will change the flux. If I change the magnetic field, then the flux will be changed. When I change the flux, or I change the magnetic field, then corresponding flux will be changed. Then an EMF will be induced and current will be flown through the circuit, and we will see that there will be a deflection of the galvanometer. Okay, so this is about Faraday's law. So how can we change this magnetic flux? The one way that I discussed, by changing the magnetic field. So here this was the B changes. Okay, then we will discuss the change in flux due to what? As we know here, that flux is BA cos theta. So by changing the A, that is the cross-sectional area of the coil, we can change the flux phi. Now we will take this example and we will discuss this. Okay, so by changing the flux, second we will discuss by changing A, or area of coil or loop, we will change flux by changing the area. How will do this? Suppose initially this is the case, that is two lines of forces are associated with a loop, and a galvanometer is connected with the loop, and there is no deflection. Okay, now what we will do is we will change the cross sectional area. Okay, so we will keep the same galvanometer, but we will increase the we will increase the cross-sectional area of the coil. Okay, and there is magnetic field lines. Suppose here is also magnetic field lines, but that is not associated with the coil. Here is also magnetic field lines, but that is not associated with the coil. Okay, so I will draw the same magnetic field lines here as well. Four lines I will draw again. So there are I keep the magnetic field constant, but here I change the cross-sectional area. This will lead to the change in magnetic flux, and this change in magnetic flux will give induction, or EMF will be induced, and this will give current. And when this current will be flown through the galvanometer, there will be a deflection of this galvanometer. Okay, so now we will discuss the third one, that is how we can change the magnetic flux by changing theta also. So now we will discuss the third factor on how we can change the magnetic flux, that is by changing theta. By changing the angle between the magnetic field and the area vector, by changing theta. Theta is the angle between the magnetic field and the cross-sectional area vector. Okay, for example, see here, this is our galvanometer circuit, and this circuit will be connected with our loop, closed loop. Okay, now this is connected like this. Suppose initially this is the case, and here the magnetic field lines are like this. These are the magnetic field lines, and the galvanometer showing zero reading, that is there is no deflection, there is no current, so there is no induced EMF. Now what we will do, we will suddenly change the angle between the magnetic field and the area vector. Okay, so we will change this. So initially what we will do is we will copy it, and we'll take the same magnetic field, galvanometer, and the cross-sectional area or the loop. Now what we will do, we will suddenly change this magnetic field within very fraction of second. If we change like this, the magnetic field is changed. So actually theta is changed, and this change in theta will change the magnetic flux, and this change in magnetic flux will induce EMF, and this induced EMF uh, will be the cause of the current that will flow through the galvanometer circuit or through the coil, and the needle of the galvanometer will be deflected. Okay, So by changing this theta, by changing cross-sectional area, and by changing magnetic field, we can induce EMF, that is electromotive force, in a closed loop. And Faraday says that whenever there will be a change in flux linked with a coil, there will be associated electromotive force or EMF. Okay, so this was actually the first law of Faraday. This was actually first law of Faraday. Now we will discuss second law of Faraday. It says the induced EMF is directly proportional to the rate of change of flux linked with a coil. So the EMF that will be induced in a coil, its magnitude is directly proportional to the rate of change of the flux linked with a coil. So mathematically we can write that suppose E is the EMF induced that is proportional to the time rate of change of flux d phi dt. Okay, even we can write the induced EMF, average induced EMF is proportional to delta phi delta t, and this one is, we can write, this is instantaneous induced EMF is proportional to d phi dt. I hope you know the difference between this instantaneous and average. Okay, now we will take example corresponding to the second law of Faraday. It says about the rate of change of flux that will be proportional to the induced EMF. Okay, so suppose like earlier, definitely I'll take the earlier cases as example. So this was our example. Here the magnetic field lines is associated with a coil, green color coil, and to measure the current or to somehow to get the measure of EMF, we can take the help of this galvanometer. Now suppose what we will do is, here there is no induced EMF. Okay, there is no induced EMF. Okay, for the time being, here for at time t is equals to t1, there is the change in magnetic field is suppose 2 to 3. Initially here was 2 lines of force, and at time t1 it gets changed to 3 lines of force, and at t is equals to t2, suppose the lines of force will be, I'll add some lines of force at time t2. There is force 5. How many? 1 2 3 4 5. Let us make it 6 lines of forces up there. Okay, so magnetic field here changes by how? At time t is equal, at time t1 the change was 2 to 3, and here the change is 3 to 6. So the change in flux is changed how many times? It is 2 times. The flux changes 2 times. So the EMF will also, as we know, d phi dt is proportional to d phi dt. So the EMF will become also 2 times. As the second law says, the induced EMF is directly proportional to the rate of change of the flux. So here the rate of change of flux is 2 times. So definitely the corresponding change in EMF will also be doubled. Okay, so this is all about the second law of Faraday. Now we will move on to Lenz law. Okay, Lenz law. What the Lenz law, it says about the direction, and it is nothing but the conservation of energy. So we will write here, it can be proved from conservation of energy. So what the law says, it says the direction of induced EMF or current, we can say, or current is such that it opposes the cause that produces it. What does it mean? It means the current is induced or the EMF is induced. The EMF has a direction, and the direction is such that it opposes that reason for which it is created. Okay, let us take an example. Suppose here we have a coil. This is a coil, and this side is the right hand side view. That is, we are looking from this side. This is right hand side view, and if we look from this side is known as left hand side view. Okay, I'll erase this eyes now. Now suppose a magnet, okay, a bar magnet. This is a bar magnet, and this is the north pole, and this is the south pole. And this magnet is, we are bringing this magnet towards the coil. Okay, what will happen? Let us zoom it a little. This will help us to visualize. Okay, so I'll now draw the lines of force, some few lines of force associated with this magnet. So this is a lines of force, this is a lines of force, this is a lines of force, this will be a lines of force, this will also be a lines of force. Okay, so now the magnet, we are bringing the magnet towards the coil. So what will happen here? The flux that will link with the coil will be increasing. Why? The reason is the lines of force, more number of lines of force will be linked with the coil. So ultimately flux will be changed. When the flux changes, the induced EMF will, there will be an induced EMF, and the direction of the induced EMF will such that, or the direction of the induced current will be such that it will oppose the cause that produces it. Who produces it, or what produces this current? This current is produced due to the motion of this magnet from this left side, isn't it? So as the magnet is coming towards the coil, that is why EMF is induced, that is why current is induced. Now the direction will be such that it will oppose the magnet. That is, the coil will repel the magnet. How it will repel? What force it can exert? That is electromagnetic force. In this case, magnetic force only. So here the current, the induced current will be flown in such a direction that it will repel the magnet. Okay. So as we know, a current carrying loop, also behaves as a magnetic pole. Okay, so suppose here the current is flowing anti-clockwise. The current is flowing anti-clockwise. We are from the out of the screen, we see that the current is being flown in the anti-clockwise direction. So in this case, the what pole it is? It is, as we know, this is north pole, isn't it? It is north pole. And when there is a current flow in clockwise direction, then it behaves as south pole. Correct? So here north pole is there in the magnet. This is coming So in the coil there should be a north pole should be induced, so that this north pole will repel this north pole. The north pole of the coil will repel the north pole of the magnet. So in which direction the current has to flow to produce a north pole facing the magnet? As we know here, it has to be anti-clockwise, isn't it? It has to be anti-clockwise. This will produce a north pole facing the north pole of the magnet. And if we see from the left hand side view, that will be the current has to flow in clockwise direction. Okay, so let me precisely mention it. From right hand side view, the current has to flow anti-clockwise. The current has to flow anti-clockwise to repel. And if you see from left hand side view, with respect to left hand side view, the current will flow clockwise. So this is all about Lenz law. The current will be flown in such a way that it will oppose the cause that it produces. Okay, now let us recap once. We first discussed first law of Faraday and second law of Faraday. In first law of Faraday, it says if there is a change in magnetic flux, there will be induced EMF. And second law says that it's all about the magnitude of the induced EMF. That is, it says about the rate of change of the induced EMF is directly proportional to the rate of change of flux associated with it. And Lenz law, what it says about? It says about what will be the direction of the induced EMF. What will be the direction of the induced EMF? That is, it will oppose its cause in such a direction. Now we can write mathematically. See, from second law of Faraday, we wrote induced EMF is proportional to d phi dt. Now, considering the Lenz law, we can write the induced EMF. Suppose it is instantaneous induced EMF was proportional to d phi dt. Now we can write it is equals to minus d phi dt. This minus sign indicates that the induced EMF opposes the cause that it produces. Also, we can write the induced EMF, average induced EMF, that is minus delta phi by delta t. Okay, so these are the formula now we have. Now we can proceed towards numerical problem based question. For that, I have already written a question. I'll solve it right now. Okay, so read the question first. It says a 800 turn coil of effective area 0.05 meters square. See, one more thing I want to mention here. So this is all about the Lenz law and the Faraday's law, but it will be multiplied by n when there will be n number of turns. Okay, so the red one was for a single coil, but suppose a system there are n number of turns, 2 turns, 3 turns, 4 turns, then it will be multiplied by the number of coil in that system. Okay, so now we will move on to the problem. The problem is a 800 turn coil of effective area 0.05 meters square. What does it mean? So the number of turn in the given coil is 800 and the effective area is 0.05 meters square. That is, we will write the cross-sectional area of the coil is 0.05 meter square, is kept perpendicular to the magnetic field B. The value of the magnetic field is 5 times 10 to the power minus 5 Tesla. Fine. But here it is written that it is kept perpendicular to the magnetic field. What does it mean? Suppose we have a coil. So first I'll draw a coil, and here the coil is shape is rectangular, no issue with that. And What is its direction? You tell me first. Its direction, the direction of the coil, area of the coil is just perpendicular to the area, and suppose the magnetic field lie on the plane of the coil. Okay, so this is the direction of the magnetic field. Now you tell me what is the angle between this magnetic field and the cross sectional area. It is 90 degree. Okay, up to this we can find out this only. Then we will move on to the next part. When the plane of the coil is rotated by 90 degree. Okay, so now the coil will be 90 degree, will be rotated by 90 degree around any of its planar axis. Okay, so we have to first consider a planar axis. So like this. Okay, this is the axis with respect to which we will now rotate the coil by 90 degree. Okay, so in this case our theta is 90 degree. Fine. In 0.1 second, within 0.1 second, it has to be rotated by 0.1 degree, the 90 degree. So the time delta t is 0.1 second. What will be the EMF induced? So our question is, what will be the induced EMF? Okay, so see, as we know, induced EMF is equals to nothing but delta phi by delta t minus delta phi by delta t. So the numerator is all about the change in magnetic flux, that is phi 2 minus phi 1, and here we have a negative sign, and in denominator how much time it took to change the flux. Okay, so phi 2 minus phi 1, let us calculate it here. What is phi 1? Phi, magnetic field, it is nothing but BA cos theta. Okay, so B is as it is, A, the value of A is as it is, the cos theta. Initially, the angle between the magnetic field and the cross-sectional area vector was 90 degree. So it was cos 90 degree, and we know the value of cos 90 degree, which is 0. Fine. Now we will calculate what is the final flux, that is BA. Let us write cos theta 1, cos theta 2. Okay, so B is as it is, A is also not changing, only theta is changing. See, when it will be changes by when the what is rotated, the plane is rotated by 90 degree. That is, the plane is rotated by 90 degree. That is, it will be with respect to a planar axis. Then the theta will be 0 degree only. It will be cos 0 degree. So finally, we will have cos 0 means 1. That is BA. Fine. But here we have to keep it in mind. Here it is not of a single turn coil. There are 800 turn. There are 800 turn. So it is better to write n times phi 2. So then we will have here n will be multiplied NBA. Okay. Okay. Now we will just substitute this value. We have a negative sign here, and phi 2 is nothing but NBA, and phi 1 is 0. I hope I am making some mistake. Earlier this was cos 90. Cos 90 means 0. Yes, let me read the questions once again. I hope this is phi 2 and this one will be phi 1. This is phi 2 and this is phi 1, and NBA and delta t here. Now we will just put all the values. Minus minus will give positive sign. The value of n is 5 times 10 to the power minus 5. The value of B is 0.05, and the value of A is what? Cross-sectional area is 0.05, and the value of the magnetic field I have written. Okay, the value of the N, that is 800. There are 800 turn is there, and the value of delta T is 0.1, isn't it? So now we have to solve this. On solving this, we will get the answer. This will be the corresponding EMF induced in the coil. Okay, so this was all about this Faraday's law, Lenz law, and the application of these two laws. Okay, thank you. I hope all you have understood this well. But if you have any doubt, do contact me through my profile in Urban Pro. See you in the next session. Thank you.